nanostructure materials, because whichever I will talk in my subsequent slides, it completely depends on the nanotechnology, because whatever the material is needed for the supercapacitor is completely based and completely depends on the nanostructure, and it's different the technology which have in the nanotechnology. Therefore, I would like to start from my presentation from nanostructure material. You all know that I was present in a previous lecture also, that where I I have seen that in many of the that eminent speaker have speak on the nanotechnology, but I would not take much time on the nanotechnology. But it is my prime privilege to discuss nanotechnology. Here, you all know about the nanotechnology, because every participant is from the faculty is here, and he or she may be PhD, or there are many faculty. They everyone knows that the nanotechnology, but I would like to just give the glimpses to the nanotechnology. And here, out of the contents present here, I will only talk on the quantum size effect. Quantum size effect is a major effect which is mostly used for the size contamination, size reduction. Therefore, here I will only briefly talk on the quantum size effect. Here, this is the quantum size effect, and then we will talk on the nanomaterial for different fields, and then we will start the supercapacitor part. Here, madam, is my screen is visible? Okay. Now, this is the you might know that this is the famous image of the nanostructure material. I will not like go to brief. The loading part is very crucial for me, because there is a less internet. Just I will go to the nanostructure material. This is a full runs. I will show the images only, because I would not like to discuss more, because you already know that this is graphene structure. When we roll the graphene, then we get a multi-wall carbon nanotubes, and when we roll up the single graphene structure, then we get a single wall carbon nanotube. This is some images. सर दिसत आहे का स्क्रीन? सर इंटरनेटचा इश्यू आहे सर. Okay, this is the quantum size confinement or quantum confinement effect. The effect of reduction on dimension on physical property. This is one of the important effect in the nanostructure material. That is size dependent effect, or is also called as a surface effect. The quantum confinement effect. This is a major part. Here, what is quantum confinement? You know that every material is having the three dimensions, x, y, and z. Let us assume that Lx, Ly, and Lz are the dimensions along the x-axis, y-axis, and z-axis, and lambda is the particular wavelength of that material. If you want to develop a nanostructure material, then we have to reduce the dimensions of the material. If we want to produce the
Hello, I think OK sir left the meeting or what? Korde sir.
Yes, sir. Okay. Now, previously we was talking on the quantum confinement. If someone want to develop one-dimensional nanomaterials, two-dimensional nanomaterials, or three-dimensional nanomaterials, then he need to reduce the dimensions. Here you can see this is a lambda. Lambda is the wavelength of that particular material. If we can reduce the dimensions of the materials along x-axis, y-axis, and z-axis, then we can reduce the dimensions of that materials to the nanostructure. Now, if the wavelength of that particular material is greater, very less than Lx, means less than nano size, or we can say that here if the dimension Lx, Ly, and Lz are very greater than the lambda, then this is a three-dimensional bulk material. If anyone want to reduce the dimension on the x-axis, if the lambda is less than the lambda is greater than Lx and Lx is very less than Ly and Lz, then you can get the two-dimensional semiconductor materials. This is the quantum well. This means you can develop the two-dimensional nanomaterials. Later, I will talk on how can reduce the dimensions and how can we get the two-dimensional materials, three-dimensional materials, and quantum dots. This is just introduction. Here, if you want to prepare the quantum wire or nanowires, then here you need to reduce the two dimensions along the y-axis and along the z-axis. Then only the single dimension is remain there. As the single dimension is remain there, then you can develop a single one-dimensional materials, and single one-dimensional material is said to be the nanowires. And if you are able to develop or reduce the three sizes, three dimensions, Lx, Ly, and Lz, then you can develop the quantum dots. This means that a spherical nanomaterials. You will see later how can we reduce the sizes of the materials and which is the possibilities or which are the synthesis technologies which is needed to reduce the dimensions of the material. Here, as you want to develop the two-dimensional material, then you need to reduce the two dimensions. There are numbers of surfactants or numbers of methods are available to reduce the particular dimensions of the materials. And this is the beauty of the hydrothermal reaction method, and we will discuss on later. Next, yesterday you might be seen that slide from the previous previous resource person that this is one of the benefit of the nanostructure material, that the surface area of the material you get a very high surface area, and I will explain this how the surface area will be increases. As this is considered as one is a surface total surface area of this is a 1 by 1 centimeters. This is a total 6 surfaces having the one cube having the 6 surfaces, and if we break this into the 1 millimeter cube, then you get a 60 centimeters square. And if you can able to develop this or break this cube into the 1 nanometer cube, then you get the this much surface area. Here from 6 centimeter square to the 60,000 centimeter square. This much surface area you got from a single 6 centimeter square when we reduce the dimensions of the materials. This is simple the beauty of the nanostructure material. Just I will give or just I have explained the quantum confinement and the surface area. These are the two major advantages of the nanomaterials, that is the material, etc., energy storage materials. Which are the some other properties I will not go in detail. Lastly, I will discuss the applications of nanotechnology. These are the applications of nanotechnology: material chemistry, medicinal, and life sciences. This is the applications of nanotechnology, electronics, and ICT. And last part, this is the most, and this is my personal part, that is I am working on the energy storage, that is hydrogen energy, energy storage, solar cell, and fuel cell. Sir, my slide is visible? Okay. As everybody knows that there is a green energy is needed everywhere, and you can see there are the cars in my present slide. You can see this, there are the cars, and these cars are charging from the charging station. And here initial is a green car. This green car is charging from the charging station. As everybody knows that there is a boom on production of energy from renewable energy resources. There are numbers of renewable energy resources. That is wind energy, turbine energy. That numbers of renewable energy resources are available is there. But out of that, numbers of renewable energy resources is there. But the storage of the energy is a major issue. Therefore, in our society, energy is the prime need, and energy storage has an equal importance as energy production. There is a survey of International Energy Storage Associations. According to that survey, in 2018, the energy storage market was US 2.8 billions, and it is forecasted to grow at 6.1% by 2026. Therefore, the total annual addition of energy from 2018 to 2026 is around 64.5 gigawatt. This means the energy market is day by day is growing. Therefore, we need an energy storage system. Therefore, we need the research in the energy storage system. There are some major issues why we need the research in energy storage system. There is a limited supply of fossil fuel, ever increasing energy consumption and growing power supply demand, renewable energy integration, decentralized energy systems, electrical vehicles and portable electronics, economic viability and scalability, and environmental friendly nature of the landscape. This is the some advanced energy storage systems. Here, electrochemical energy storage system, chemical energy storage system, biological energy storage systems, mechanical energy storage systems, electrical energy system, and thermal energy storage systems. If anyone want to carry out research in the energy storage system, there are numbers of options to perform the energy storage devices. Here I have explained this all numbers of the energy storage systems. If anyone want to develop the electrochemical energy storage system, then there are flow battery, rechargeable battery. If anyone want to develop biological system, then there is a glycogen and starch energy storage systems are there. If anyone want to develop the mechanical energy storage system, then flywheel, hydraulic accumulator, fireless locomotive, and if anyone or the electrical energy storage system included the capacitor and supercapacitor. The numbers of energy storage systems are there, but out of the numbers of energy storage systems, there is a special criteria on which you can choose, or you can say that there are the major criteria on which the energy storage system is depend. Every energy storage system must have high energy density, fast charging and discharging rate, having the long cycle life and durability. It must have the cost effectiveness, and most essential part, it should be the safety and the having the environmental impact. Therefore, the high energy density is a crucial need for every energy storage system. As I have discussed the earlier energy storage system, so whenever you will pointing out the energy storage system, you must see, or anybody need to discuss how much the energy storage system giving out the energy density, then how much this energy system giving us the power density and the life cycle of this energy storage system. These are the special criteria for the every energy storage systems. As I am working on the electrochemical energy storage system, and here these are the special electrochemical energy storage systems are there: battery, supercapacitor, and fuel cells. These are the specification of the battery. Battery having specification as a capacity, ampere into hour, voltage, cycle life, energy density, charge discharge rate, or this is also called as a C rate. Whenever you move over the capacitor can be identified on the basis of capacitance, voltage, power density, equivalent series resistance, and cycle lives. And when we move towards the fuel cell, then fuel cell can be identified on the basis of power output, efficiency, operating temperature, fuel type, and startup time. These all are the research area in the energy storage system. If you take the battery, supercapacitor, or fuel cell, you need to specify this energy storage system on that particular specifications. Therefore, if you able to increase the capacity, voltage window, cycle life, energy density, and charge discharge or C rate of battery, then you can publish or you can get your result into the publication. And there are also the supercapacitor. In supercapacitor also, if you are able to increase the capacitance, voltage window, power density, equivalent series resistance, and cycle life, these are the some points or specification that in which there is a continuously research is going on. Also, in similarly into the fuel cell. I would like to discuss the comparison of energy storage system on the basis of their specification and how the battery, electrochemical capacitor, and electrolytic capacitor, that is supercapacitor, different from each other. As you can see in the window, sir, is my slide is visible? Okay. You can see the specification has here battery. You can see the discharge time of the battery is 0.3 to 3 hours. Where you can see the discharge time for the electrolytic capacitor 10 to the power minus 3 to 10 to the power minus 6. This is around the microsecond. And if you see the discharge time of the capacitor, it is around the 0.3 to 30 second. If we see the discharge time for the discharging time for battery is around 1 to 5 hours, and you can see for electrolytic capacitor around 10 to the power minus 3 to 10 to the power minus 6 second. And for supercapacitor, you can charge this supercapacitor from 0.3 to 30 second. You are observing the major differences. As you can see, the energy density of the batteries, it is around 10 to 100, and electrolytic capacitor is very less energy density, and the capacitor has the energy density around 1 to 10. Therefore, the charge discharge efficiency, this is the charge discharge efficiency of this battery around 7 to 0.85. This is around 1, and this is nearly same as the battery. Cycle life battery of the battery is 500 to 2000, and it is more than 5 lakh, and it is more than 1 lakh. And this is the discharge time for the battery, electrolytic capacitor, and electrolytic supercapacitor. Electrostatic supercapacitor means that capacitor you can use in electronic equipment. You may have seen this supercapacitor. You may seen the electrostatic capacitor. Energy status of the energy storage, there is a Ragon plot. On the basis of Ragon plot, you can distinguish or you can see the status of energy storage system, that is capacitor, and fuel cell. Here you can see the supercapacitor. Supercapacitor having a moderate power density and moderate energy density, whereas the electrolytic capacitor has a very high power density and very less energy density. And this is the battery having the very high energy density but having the very less power density, and fuel cell having the high energy density and having the very low power density. This is the Ragon plot, which gives us the status of your designed energy storage system. Whenever you will design or we will design any energy storage system, we need to draw this plot, and when we plot, we have to plot our result, and in which region our graph showing their results. That is, if the region your result showing the result showing this your result showing the power density around this region and energy density around this region, this means you may say that your material is working as a supercapacitor. And if your material showing the higher power density but less energy density, then you can say that your material has a characteristics of the capacitor only, that is the electrolytic capacitor. And if your material is having the very high energy density but having a very low power density, this means that your material is suitable for the battery applications. And if your material has a very high energy density but very less power density, then your material is suitable for the fuel cell application. This Means you can assign, or you can assign the properties to your material, that your material may be working for which part of this Aragon plot. Yes, sir. Yes. Here, sir. Okay, okay. This side, sir. This. Okay, sir. Okay, sir. Okay. In generally, in case of the any paper which is published in the is published for the supercapacitor study or any energy storage study, this Aragon plot is a very essential part. This Aragon plot shows that, or this Aragon plot gives you the idea that your design material or your synthesis material is working in which part or in which applications. For any energy storage material, this material has particular power density, and any material has a particular energy. If you have calculated the energy density and power density of the material, then you need this plotted graph is said to be the Aragon plot. This Aragon plot is the graph between energy density and power density. When you plot this graph for your material, that time your graph is particularly placed in a particular position of this graph. Suppose your plotted graph is positioned at capacitor region, that is having the very high power density but very low energy density. This means suppose that you, sir, माझा तुम्हाला arrow दिसत आहे का sir? As you can see my arrow here, if your material is placed at capacitor region or this region, then here suppose your material results as placed at this point, then you can say that your material has a very high power density but having a very low energy density. This region has a very high power density but very low energy density. That time you can say that, or you may predict that your material is not suitable for battery and fuel cell application, but your material is having the very high power density, then you can put your material for the capacitor application, or you can assign your material for the capacitor application, that is the electrolytic capacitor application. As battery needed very high energy density, or battery has a very high energy density but very low power density, this is specification of the battery. If the material is not giving you the very high power density but giving you the very high energy density, then at time you say that your material is not suitable for the capacitor application, but your material is suitable for the battery application. But supercapacitor is a moderate, for it having the moderate energy density as well as moderate power density. Therefore, if your material is working in specific that region, or your material showing the result of energy density and power density having very moderate power density and having the moderate energy density, then if your results are placed or obtained at these regions having 0.1 watt hour kilogram, watt hour per kilogram, and power density into the watt, this particular 10 to the power 4, from 10 to 10 to the power 6 to the 10 to 10 to the power 10 energy density, means, or if your material get the energy density of around 10 watt hour per kilogram, then you can say that your material has a supercapacitor property. This means this Aragon plot is useful for identification of the materials, and this is also useful for identification of the any type of material, that is battery material, fuel cell material, or a capacitor material. And on that basis, you can identify your material and you can predict your results. Clear, sir? Okay. Now, this is a battery. There are batteries, and we know that there are two batteries: metal ion batteries and lead acid batteries, which are conquer the market. In whenever you are go to the market and you will ask the battery, then they may give you the lead acid battery, or they may give you use the metal ion batteries. But metal ion batteries, this means metal ion battery means lithium ion batteries, sodium ion battery, and numbers of battery, magnesium ion batteries. There are numbers of metals ion batteries, but out of that numbers of metal ion batteries, lithium ion battery is more famous, and it is readily available in market or everywhere, or in our mobile also. But for metal ion batteries and lead acid batteries, there are numbers of shortcomings. Which shortcomings are there? We will discuss later here. The metal ion battery has a limited energy density. It having the safety concern. It has a very limited lifespan, having the low resource availability, having a very large charge time, and these materials are the temperature sensitive. As we move toward the sodium ion battery, this sodium ion battery having the very high it needs the very high temperature, and it needs the special material to that is special shelf materials, and it's having a very high cost. Whenever we move toward the lead acid battery, the lead acid battery has a major problem of weight and size. It has also the limited energy density. It is also have the shorter lifespan. It having the low, very slow charge and discharge rate. It is also the is require maintenance, and as it contains lead, this lead has a very huge environmental impact. That is a very diverse environmental impact, and self discharge rate means this battery is selfly discharged without using any external load. When there is no external load, this battery get self discharge. These are some major issues. That major issues pointed out us to discover new materials or new types of technology. Therefore, considering these shortcomings from last 20 to 30 years, there is a one initiative of the green energy storage that is called as supercapacitor, and this supercapacitor emerged as a green energy storage device. Why this supercapacitor is said to be the green energy storage device? This is the some advantages of the supercapacitor over the battery and lead acid battery. Here, the supercapacitor has a high power density, that is rapidly energy delivery and absorption. This means this material has absorbed very quickly, is absorb very ions very quickly and deliver this energy into the rapidly deliver this energy. The material which is needed for the fabrication of the supercapacitor is a low cost. This means even by using the ZNO, you can also build up the supercapacitor. This means that the supercapacitor has a very low cost raw material is required for the fabrication of the supercapacitor. It has a pulse energy supply. This means this gives you the very intense energy supply. Whenever you need very intense energy, that time you also use the supercapacitor. And whenever you need very small amount of pulse of energy, then you can also use the supercapacitor. This means there is a diverse application of the supercapacitor for intense energy and small energy. That means intense. You may don't know that whenever we will start our car, that time we need very high amount of high pulse of energy. There also you can use the supercapacitor. Therefore, supercapacitor has a very pulse energy supply. This is ideal for application needing quick burst of power. Supercapacitor has a very long cycle life. It maintains performance over many charge discharge cycles. It has a lower maintenance cost, reduced need for frequent replacement, higher reliability and safety. It is environmental in nature because as there is no use of very poisonous materials as lead or other lithium or any other material, this means that you can use this supercapacitor as a green energy storage device and rapid energy storage and release. This is a perfect for quick response applications. These are some basic advantages of the supercapacitor over battery and lead acid battery. Also, specific advantages over the battery. As compared to the battery, it has a lower maintenance cost, having high power density, having two order of magnitude higher than the batteries, higher reliability and better safety than batteries, supply significant energy in pulse means it having the more energy density than that of batteries. Battery has a very high energy density, but this high pulse power. It has the ability to store and release the energy within the time frame of few seconds. Also, it having the long cycle life, which having the three order magnitude longer than the batteries. There are here, this is the classification of supercapacitors. Broadly, the supercapacitor are classified into the three types of devices, that is electric double layer capacitor, EDLCs. The short form of the double layer capacitor is EDLCs. Usually the EDLCs is preferred to say in the electric double layer capacitors. Second with the pseudo capacitors, and third is the hybrid capacitors. This is the categorization or the differentiation of the supercapacitor, or we can say this is differentiation of supercapacitor is on the basis of the material or electrode material is used for the fabrications. If you have fabricated your electrode from porous carbon, single wall carbon nanotubes, or multi wall carbon nanotubes, reduced graphene oxide, or aerogel, then your designed supercapacitor is belongs to the EDLCs. If you have fabricated your supercapacitor by using transition metal oxide, hydroxide, sulfides, vaccine, or conductive polymers, then the fabricated device is said to be a pseudocapacitor. Means on the basis of their energy storage mechanism, transition metal oxide has a different energy storage mechanism. Porous carbon, single wall nanotubes, or carbon-based material has a different energy storage mechanism. And if you use both carbon materials as well as metal oxide, metal sulfides, mixins, or conducting polymers into the same device, then this device is said to be the hybrid capacitors. That is composites of carbon with transition metal oxide, hydroxide, sulfide, mixin, and conducting polymers. Here, on the basis of electrode material as well as the type of energy storage in the electrolyte. When we use the electrode into the electrolyte, there is a different storage mechanism in electric double layer supercapacitor, pseudocapacitor, and hybrid capacitor. One by one, we will move toward the which type of mechanism will be in the EDLCs, pseudocapacitor, and hybrid capacitor. This is the applications of supercapacitors. Here is no need to explain in deep. There is a application in transportation, renewable energy storage, consumer electronics, industrial applications, aerospace and defense, medical devices, smart grids, telecommunications, electronic devices with high power requirements. Here, I would like nowadays this supercapacitor is broadly using renewable energy resources for storage of renewable energy. As everybody knows that, as everybody knows, whenever there is a production of energy from renewable energy resources, sometimes there will be the, suppose let us consider there is a production of energy from wind turbine. As wind turbine is completely depends on the mood of the nature. Suppose that sometime there is a very huge amount of air into the environment. That time this turbine gives you large amount of energy, and this large amount of energy you have also you need to store this large amount of energy into the your energy storage system. But sometimes there is a small amount of air will be passing around the turbine. This turbine will moving slowly. That time very less amount of energy will be produced by the turbine. Even different in the turbine from small amount to the very huge amount. Therefore, want much amount of energy to your energy devices. You need a smart grids. Therefore, supercapacitor nowadays, in case of a renewable energy storage system, there is a huge application of the supercapacitor. Means they are demanding more supercapacitor for storage of energy, because supercapacitor has a capacity to store very less, even smallest amount of energy. And when we multiply the supercapacitor, then you can store very large amount of energy. Therefore, in place of batteries, there is a huge amount of production, huge amount of use of the supercapacitor in a renewable energy storage system. challenges in supercapacitors. Which challenges recently we facing on the supercapacitor? Particularly as I'm speaking on, there is a more energy density and there is a huge amount of energy storage, but still the supercapacitor obtained is having not much amount of energy, having not get very large amount of energy supercapacitor. Supercapacitor which we have got that is storing very low energy density for a very small time. Therefore, supercapacitor has a low energy density. The produced supercapacitor has a very high cost and having this is due to the high cost of materials, having the low surface area, active materials as electrode in supercapacitor, low porosity of the active materials, and low intrinsic conductivity of the active materials. As supercapacitor is fabricated from the uh, transition metal oxide, this transition metal oxide does not have that much of electrical conductivity. Therefore, these issues are arising here. This is low energy density, low surface area, low porosity, and low intrinsic and high cost of the supercapacitor. These are the major challenges in a supercapacitor to make the supercapacitor to familiar with us. Now, as I have earlier talked on the nanotechnology, which nanotechnology gives us the benefits for the application of supercapacitor. These are the benefits of the nanostructure material in energy storage. Nanostructure material has a high surface area, therefore it can be used as electrode material. It having the high electrical conductivity. Nanostructure material having the high electrical conductivity, having the shorter ion diffusion path. It having the enhanced mechanical strength and stability. Nanostructure material has a flexibility and lightweight. Therefore, this flexibility and lightweight is also used for design the lightweight battery. With the help of nanostructure material, we can tailor the pore structure of the materials. This means we can tailor the pore structure of the materials. Nanostructure materials are the chemical and thermally stable. It having the electrochemical stability and diverse opticals and having the diverse materials options. This means that nanostructure is mostly beneficial for the production of the area, hybrid materials, and shorter ion diffusion path materials for the battery application or supercapacitor application. Now, we moving toward the inner part of the supercapacitor materials. These are the key elements of the supercapacitor. If anyone want to build up the supercapacitor, we need electrode, electrolyte, separator, current collectors, and packaging and terminals. Electrodes are positive electrodes and negative electrodes. Here, the positive electrode is made up from transition metal oxide, hydroxide, sulfides, mixing, and conducting polymers. Negative electrode is usually made up from activated carbons, but sometimes it also can be made up from metal oxide. Electrolytes used as organic electrolytes and aqueous solution or organic solution into the lithium, sodium, and potassium. Again, as I am working on the electrode material for supercapacitor, I would like to show you the last slide that here the porous material carbon, single wall nanotubes, carbon nanotubes, transition metal oxide, metal sulfides, and metal. These magazines, conducting polymers, and hybrid capacitors. Here, this is the material that is used as an electrode material for supercapacitor. Now, when you want to design the supercapacitor, there is a numbers of synthesis material for production for the synthesis of the electrode material for supercapacitor. This is the sol gel method for production of or synthesis of electrode material. You can use sol gel method. Sol gel method has a versatility and control over purity. You can use chemical vapor deposition method, physical vapor deposition method, ball milling, and electrochemical deposition. Also, you can use hydrothermal synthesis, grain synthesis, chemical precipitation, microemulsion, and temperature assisted synthesis. In our work, we have using the hydrothermal synthesis method. Therefore, which are the major advantages for using the hydrothermal synthesis method are these are the hydrothermal synthesis method. In hydrothermal synthesis method, you can control over the nanostructure morphology, uniform particle size distributions. Using the hydrothermal synthesis method, you can enhance the surface area. You can tailor the crystallinity of the materials. You can improve the conductivity of the materials. Hydrothermal method nothing but the cost effective and scalable method. And again, hydrothermal method is the mild reaction condition. This means hydrothermal method can be worked on the moderate temperature. This is the synthesis or simple synthesis method for the synthesis of the electrode material. Correct, sir? Hello. हाँ सर, मदत ब्रेक घ्यायचा आहे का? ब्रेक घ्यायचा आहे का म्हटलं मदत? कंटिन्यू करायचं आहे का? विनंती करतो, तुम्हाला जर मदत प्रश्न असेल तुम्ही विचारू शकता. ओके. ओके, ओके. ओके, ठीक है. येस सर. Experimental setup for the hydrothermal synthesis. For the synthesis of for the synthesis of electrode material, there is a very simple hydrothermal synthesis method. Just you need the hydrothermal reactor here. This is our one of the synthesis strategy which we have used for the production of CU nanoflowers. This is you need only magnetic stirrer and one hydrothermal reactor. The centrifuge. This is centrifuge machines, and at as earlier we have discussed, this hydrothermal synthesis need the mild reaction condition. Then this means that up to 120 degrees Celsius to 150 degrees Celsius, you can synthesize the nanostructure material using the hydrothermal reactor. Using this hydrothermal synthesis, we have synthesized this three-dimensional nanostructure material. We have also synthesized this NiCO2O4 nanosphere. This is a nanoballs having the size of 67.4 nanometers to the 37.7 nanometers. Also, by using the same strategy, hydrothermal synthesis, we have synthesized these nanorods, and having these nanorods having the size around 10 to 20 nanometers. Here you can see this is also the we have synthesized nanorods. This is around the 200 nanometers. You can see the tame images of the nanosphere is around the 20 to 22 nanometers in range. This is the set patterns of NiCO2O4 material. Also, using the same strategy, we have synthesized this cauliflower-like structure. This is the work of our my collaborator, that is Dr. Mardikal sir. He has synthesized these nanoflowers using the hydrothermal reactors. We collaboratively working on these materials for supercapacitor applications. Now, once you synthesize your materials by using the hydrothermal synthesis, you need to fabricate the supercapacitor electrode. This is the strategy, or this is the flow chart showing you how can you fabricate the electrodes. This is a very simple method for fabrication of the electrode for supercapacitor. For any supercapacitor application, you need the substrate, and the substrate is used for the supercapacitor fabrication is a stainless steel substrate, which having the 304 grade. As stainless steel is a very low cost material, it is readily available or easily available anywhere in the market. You can say you can ask for the 304 grade stainless steel material. This you get this around 100 rupees. Then you use the active materials, that is you have prepared the hydrothermal material that is said to be the active materials. You add 5 weight percent acetylene black and add 5 weight percent conductive additives, that is PVDF. Then dissolve this mixture into the DMF, dimethyl fluoromidite, and add this slurry into the stainless steel substrate by using the doctor blade, and dry this at a 60 degree in an oven, and then use this electrode for electrochemical analysis. This is a simple strategy, or this is a simple flowchart that explains the fabrication of electrode for supercapacitor. Now, when you want to electrochemically analyze the supercapacitor electrode material, you can analyze this supercapacitor electrode material by single electrode, as you can analyze this electrode material using 3 electrode setup as well as 2 electrode setup. Later I will discuss how to analyze this electrochemical electrode using the 3 electrode 2 electrode initial. Now I will discuss the 3 electrode setup. Here you can see 3 electrodes are there. Here this is a black, blue and red. In 3 electrochemical setup, we need 3 electrodes. One is the reference electrode. Usually AgCl is used as a reference electrode. One is a counter electrode, that is a platinum is used as a counter electrode, and one is the our active electrode, or electrode made up from the active materials. Active materials means the material that you have developed for your supercapacitor applications. This is a working electrode. This means working electrode, a reference electrode and counter electrode. Counter electrode is nothing but the platinum. This is a inert electrode. Once you have developed your electrochemical cell, then you need to add electrolyte. Usually Na2SO4, KOH, or H2SO4 is also used as an electrolyte. Acidic or basic you may use as per your requirement. You can use the electrolyte for the electrochemical testing. Once this electrode is or cell is set up, there are initiation of the energy storage mechanism. Here, in case of electrostatic, you can see this is positive electrode, this is negative electrode. Here, by electrostatic process, you can store here energy gets stored. In electrolytic capacitor, the process of electrolytic, here the energy gets storage. But in case of supercapacitor, by formation of electric double layer, energy gets stored. Here, this is a particular theory of electrochemical energy storage. Here, this is a negative ions. Number 1 showing that inner Helmholtz layers, here outer Helmholtz layer, this is the outer Helmholtz layer, this is 2 numbers showing the outer Helmholtz layer, and this 4 numbers showing the solvated ions, and 5 and 6 showing the specially absorbed ion and solvated molecules. This part from 1 to 3 showing the electrolyte material, and this is your substrate, and here this black line showing you the electrode material that you have deposited on your substrate. In case in a electrolyte material there are numbers of ion, that is positive and negative ions will be in your electrolyte material. When you charge your electrode, that is, let's assume that you charge your electrode, you starting the charging to your electrode, that time negative ions will be deposited or develop on your negative electrode. That time simultaneously the positive ions will moving towards your negative electrodes, and once the positive ion moving towards your negative electrode, that time there is a formation of diffuse layer. In next slide you can see this is the actual charged supercapacitor. Here this is the electrolyte part, and here you can see this is positive negative porous electrode material, and here there is a development of the charges. Basically, in case of the supercapacitor, there is a formation of double layer. This is positive and this is negative. This negative and positive, negative and positive. There is a formation of double layer. This double layer gives you the pseudocapacitance. Specifically, absorption ion gives you the pseudocapacitance. Therefore, here this is formation of pseudocapacitance in a supercapacitor. This means if you use the metal oxide, you get a pseudocapacitor. And if you use the EDLCs, then if you use the reduced graphene oxide, then you get the EDLCs. In our research, we have used the spinel transition metal oxide NiCO2O4 as a electrode metal for supercapacitors. These are some specifications of the NiCO2O4 supercapacitors, as it is high electrical conductive, easily available, cost effective, environmental friendly in nature, and high chemical stability. We have reported here this case study for NiCO2 nanostructure material. We have synthesized this NiCO2 for using nickel salt and cobalt salt at 60 degrees Celsius using hydrothermal reactor, and we have used this reducing agent urea and template, that is we have used the PEA ethoxylate. We named this NC1 for the material prepared for 60 degrees Celsius, and we use NC2 for prepared material at 80 degrees Celsius. We use NC3 for 100 degrees Celsius, and when we use NC4 for 120 degrees Celsius. This is the XRD of the material. This XRD shows that the successful synthesis of the NiCO2 materials. You can see the same materials. This is the FESM of the materials. This shows that cauliflower-like and spherical morphology of the synthesized materials. Also, you can see this nanorod structure of the NiCO2 synthesized at 60 to 120 degrees Celsius. This is the BET surface area of the NC1, NC2, NC3, and NC4. You can see the surface area for NC1 is 21.28, 73.7, and NC3 for 108.42, and for NC4 24.94. Here you can see the pore volume. The pore volume is a very essential part for the energy storage material, because we need such pore volume, that means that can store the electrolyte ions. When we said to be the material is a very useful for the supercapacitor application, that time the pore size should be the ion size of the electrolyte. Here this is a average pore size. Here this is a 53.21, 40.35, 43.91. This is the average pore size of the material. This is, you can see the high surface area given to the NC3 material. These are the FTR analysis, and now this is the electrochemical characterization of the NiCO2O4 material. Using, this is a cyclic voltammetry. This cyclic voltammetry is used to assign or used to estimate the energy storage capacity, specific capacitance into your materials. This is a electric cyclic voltammetry is obtained potential versus current density. It is usually carried out at a different scan rate from 5 to 100 millivolts per second. By using the surface, using the area of this CV curve, you can calculate the specific capacitance. Here you can see at scan rate 5 millivolt second inverse, you get the specific capacitance 145.2. For the NC1 sample, you can see NC2 for 263.1, NC4 250.1, and this is the specific capacitance obtained at a scan rate 5 millivolt second inverse. As the scan rate increases from 5 to 100, the specific capacitance is going to decreases. Here you can observe that we got higher specific capacitance at NC2 sample, but in previous slide you can see that here we got a very high surface area for the NC3 samples. Someone may say that this is a controversial, or anybody can say that has the high surface area, NC3 has a high surface area, then it may give us the very high surface, very high specific capacitance. But specific capacitance is not only depend on the surface area, but is also depend on the pore size and pore volumes. If you got a very high surface area, but as you know that carbon material has a very high surface area, but only the single carbon materials cannot be used both any positive and negative electrode for the supercapacitor fabrications. This means that metal oxides, or we need any other metal oxide, sulfides, or any other materials to composite with the carbon material so that it may store high energy. It gives high energy by storing the numbers of electrolyte ion into the pores available into the carbon materials or the metal oxide materials, as well as it can give us the high energy density. This means that here you can see that difference at 5 scan rate, 5 millivolts per second scan rate, you get a high specific capacitance for the NC2 sample, even though this NC2 sample having the less surface area. This is another characterization for electrochemical assignment of the energy storage, energy density and specific capacitance. Using the galvanostatic charge discharge, you can calculate the specific capacitance, energy density, and power density. Here, using the discharge time, here this is the discharge time and this is the charge time. Using that discharge time, you can calculate the specific capacitance, energy density, and power density. Here you can see this energy density, the NC2 sample is 5.43 and NC3 sample has 216.30 and energy density is this much. Here this is a variation of specific capacitance with scan rate, and here is a variation of specific capacitance with the current density. This is again the Ragon plot. As I earlier discussed that you can assign your material, whether it is supercapacitor, whether it is a capacitor, or whether it is battery material. If you got the energy density and power density Ragon plot around this middle region, then you can say that your material is suitable for the supercapacitor. Again, this is a cycle number test for capacity retention versus cycle numbers. We have carried out our material for 1000 cycles and we got the capacity retention of 95.34. Also, the next important characteristics for the supercapacitor is the impedance, electrochemical impedance spectroscopy analysis. Here, this is a Nyquist plot. This is Z dash versus Z double dash. Using this intercept at the x-axis, you can estimate the electrolyte resistance, and the diameter of this curve. This diameter of this curve gives you the charge transfer resistance. In NC1 has a electrolyte resistance 0.89 and charge transfer resistance is of 5.42. This is versus the electrolyte resistance and charge transfer resistance obtained for the electrolyte NaCO2O4 electrodes prepared at different temperature conditions. Scopes and prospect of the supercapacitor. The supercapacitor has a very wide scope for research. Anybody is preparing material, then it has a scope for study its property as an electrode material for a supercapacitor. There is a scope for development of energy density. We can use different materials and we can modify materials by doping, and we can analyze this material for supercapacitor applications. We can use different hybrid systems, different hybrid materials, that is, you can combine different polymers, carbon materials, as well as metal oxide, metal sulfides. You can make composite and you can test these hybrid materials for supercapacitor applications. Once you fabricate the supercapacitor, then you can fabricate flexible supercapacitor for different variable devices. That is, you can design small battery like supercapacitor, coin cell like supercapacitor. You can develop pouch cell supercapacitor. This may be the flexible supercapacitor. There is a more advancement in manufacturing processes of the supercapacitor. You can you can check your environmental impact of the supercapacitor. You can integrate your supercapacitor with any other electrical devices. This means you can integrate with your supercapacitor to the renewable energy system, and you can make the electrical engineering to the supercapacitor. These are the scopes and features for the supercapacitor. This is the YouTube link. I will not show this YouTube link how to fabricate supercapacitor. I will hand over this slide to the convener of this STTP. Then you can watch this YouTube video. This is also the how to fabricate the battery. Battery also you can fabricate using these materials, but battery fabrication need a glow box, so it is very difficult to fabricate battery at the lab which having the low infrastructure. I would like to acknowledge my research guide, my collaborators, Dr. J.N. Chaudhary, Dr. Yogesh Kumar, Dr. A.K. Thakur sir from IIT Patna, Dr. Yogesh Baisla, that is battery